lecture number 3 this week. Before now, we've looked at 2 topics. Okay, so let me just come here. Okay, so here, if I do this over here. Okay. All right, prior to this class, in week 1, we looked at stress. And under this, we looked at internal loadings, which is basically the fundamental of internal loadings, which is fundamental of statics. Then we went further to look at stress. And here we divide stress to normal stress and shear stress. Then in week number 2, I think in week 1, we only stop at normal stress. So week number 2, we looked at shear stress. Then we went further to look at strain. This is 1. And number 2, we looked at strain. Is that correct? You can just chat with me. I'm going to be online, so you can chat with me. But just for me to know that you are in my class, I need responses. Else I'll just be talking like a radio. You know what a radio is? Radio. Oops. Radio. Just talk, no response. So I don't want to be like a radio. Okay. Okay. Until normal strain, sir. Are you sure? Under strain, I looked at 2. I look at normal strain. And I look at shear strain. I covered everything in your last class. I covered everything in your last class. I covered all the lecture notes. I did one example on shear strain, and I asked you to try one other example. In your last class, I have an example. I say, try this. I remember saying in your last class that shear strain, I said, is change in angle. And I say your shear strain is gamma, which is your original angle to our final angle. And I said most times your original angle is 90 degrees, which is pi all over 2, because your shear strain is in radians, minus theta f in radians. And we have one example we solve in that class. So, Batria, you may have to go and do some little revision. Okay, thank you very much for responding. That's very good. Okay, so what I'm going to do today is I'm going to continue from where we stopped last time. So today I'm going to take another topic. So I'm going to delete all this now so I can have somewhere to write. And like I always tell you, my class is more interactive. So I want you to interact. When I ask questions, I want a response. So here we are in week number 3. And in week 3, I'll be looking at mechanical properties of material. Mechanical properties of material. Now, I have 3 materials here. I want you to differentiate for me what are these different types. Can you see this? Or let me do it like this so you can see how it looks. Can you see this? What type of material is this? What type of material is this? Pardon me? Wood. Okay, wood. Thank you. Now, what about this? Can you see this?
Plastic.
Okay, so we have wood. Note it down. We have wood. We have plastic. What about this?
Metal.
Okay, this is a metal. All right, now we have wood, we have plastic, and we have metal. What do you think is the difference between these 3 materials? What do you think is the difference between these 3 materials?
The strength of
material.
The strength of the material. When you say strength of the material, what do you mean?
The deformation.
Okay. So basically, we said the difference between these three materials is the strength. For example, if I apply a load on this, it is difficult for me to bend this. If I apply a load on this, the only difference is just the strength. If I apply the same load on this, I'm going to break it into two. So what we'll be looking at is the strength. And what constitutes the strength of your material is the mechanical properties of the material. What constitutes the strength of your material, what makes up the strength of your material is the mechanical properties, the composition. What are the mechanical composition of this material? So yes, the difference is the strength, but what constitutes the strength is your mechanical property. So that's what we're going to be looking at. We'll be looking at the strength of your material. How do I determine the strength of my material? Now, if you look at this, we say this is harder than this. Is that true? This and which one is stronger? This and this.
Metal.
This metal is stronger. Why? Because of the strength of the material, because of the mechanical properties of the material. So that's what we're going to be looking at today. So today we are looking at mechanical properties of material. Right, so I'm just trying to look for something here. I used to have some things here, but I don't think I can find the one. Please, if you are not following us, let me know so we can explain to you separately. All right, so okay, that's all right. So let me take up. So, like I said, today we are looking at these is in all my classes. There are things I expect you to know at the end of the class. So what I expect you to know at the end of this class? What do I expect you to know at the end of this class? Number one, you should be able to differentiate between elastic material and plastic material. Differentiate between elastic and plastic deformation of materials. Number two, you should understand how to measure the strength of material through experiment. If we carry out an experiment, how do I determine the stress and the strain of this material? And number three, based on the stress and the strain of the material, how do I determine the mechanical properties of the material? Say, for example, I measure my stress and strain, and I have this stress strain diagram. This is stress and this is strain diagram. On this diagram, how do I determine the properties of this material? What are the properties that are of interest? Number one, Young's modulus. So these are the mechanical properties we'll be looking at, Young's modulus. And you use E. Then you look at your yield stress, sigma YP. You look at your UTS, ultimate tensile strength, sigma UTS. Your UTS is ultimate strength, ultimate tensile stress or strength. You can use stress, you can use strength. It's ultimate tensile strength, both bullet, UTS. Then you look at your failure stress, and that's sigma F. So on this diagram, how do I determine all the properties? So all those things you should be able to do at the end of this class. At the end of this class, every one of you should be able to differentiate between elastic and deformation. Then number two, you should be able to understand how to measure the stress and strain through experiment. And number three, you should be able to correlate the properties of some engineering materials to their stress strain diagram. And I've given you few of the properties you need to correlate here. We are looking at the Young's modulus. You are looking at the yield stress. You are looking at the UTX, which is the ultimate tensile strength or ultimate tensile stress. It's okay. Then you are looking at the failure stress. Okay. So when you talk about strength, like we said, like we all agree at the beginning, that the difference in those material is the strength of the material. So what is the strength of material? The strength of your material is the tendency of your material to withstand applied load without any deformation. Like I illustrated earlier, if you look at this, a load and a load on this. So from your judgment, which one has more strength? Hello? Can they still hear me? Okay, are you hearing me?
Yes,
Your
sir.
line
Yeah.
is slow.
Yes, sir.
Okay. Now, like I said, I'm talking about the strength of material. And I said the strength of your material is the tendency or the ability of your material to withstand applied load without any deformation. For example, I have this metal here. I'm applying load on this. I cannot feel anything. Now I have this plastic and I'm applying load. So among these two materials, which one is stronger? Which one has more strength?
Metal.
This has more strength as compared to this, which is just the tendency or the ability to withstand load without any deformation. Many materials, when in service, when in use, they are subjected to different force or load. So when you are using them, when in use or in service, the property of a material reflects the relationship between the deformation and the applied load. Like we said the metal is stronger because it's not deforming when we apply the load as compared to this. And is a function of the property of this metal as compared to the property of the plastic. So basically, the property of your material reflects the relationship between deformation of the material of force. So very quickly, I'll be looking at the difference between elastic deformation and plastic deformation. When you apply a load, when you apply a load on your material, there are two things you experience. One, you can experience elastic deformation, and two, you can experience plastic deformation. Now, I'm going to illustrate with a few things here. Now, a ruler, if I apply a load at this point, there is deformation, is that right? Hello?
Yes, sir.
Yes.
Okay. Please,
Yes,
if you
sir.
don't respond, if or not. So I need a response when I ask questions, please. Okay, you have this ruler here. Applying a load here. What do you observe?
The ruler is bent.
The ruler is bent. Now I take off the load. What happens?
Release.
Now I take off the load. What happened to the ruler?
Original
Back
shape.
to
It's back to its original shape. Thank you. So elastic deformation, when you apply a load, there's going to be deformation. When you take off the load, it's back to original shape. Another good example is this. You can see this. This is a rubber band. I apply a load, it increases. I take off the load, it goes back. So elastic deformation is when you apply a load, there is deformation, and when you take off the load, it returns back to original shape. Elastic deformation is a deformation in which the material returns back to its original position after the load acting on the material is removed. Here, I apply a load, it increases. I take off the load, it goes back. Same thing here, I apply a load, it changes, is bent. Take off the load, go back. So that tells us that the deformation here is temporary, because when you take off the load, it returns back. It's not a permanent deformation, and it's reversible. Atas bawa, goyang, it's reversible. You do back and forth, it's reversible. So for elastic deformation, it's reversible and it's temporal. So the first thing you need to understand here is this material return back to original position after your load is removed. So you must know that. Faham ta faham?
Faham, sir.
Understood, sir.
Okay. So then the other one is plastic deformation. Plastic deformation. What is plastic deformation? Now, you can see this. This is another plastic, but it's different from this one because the material is different. As in the properties are different. Now I apply a load on this. What did you observe?
It breaks.
There's a
Broken.
deformation. There's a deformation. Now I'm trying to take off the load. Can it go back?
No.
No.
Okay.
No.
So
No,
for
sir.
plastic deformation, when you take off the load, cannot go back to original position. Elastic, belay, badly, original position. Plastic, tabule, cannot go back. So for plastic deformation, is a deformation in which a material cannot return, tabule, cannot return to its original position after the load acting on the material is removed. So on this, now there's a permanent deformation. Anytime you come to my office, you see this permanent deformation here, cannot be removed. So for plastic deformation is permanent. There's going to be a permanent dent on this. And it's irreversible because you cannot take this back to original position. So plastic deformation is permanent and is reversible. And like I said, for plastic deformation, the material cannot go back or return back to original position after the load is removed. Faham, ta faham. No, I'm not sure when you write. So are we together? 12, 18. Okay. I just want to make sure all my students are okay. That's why when I say anything, I need to call you. I need to stop and ask questions if there's any problem. And please, if you have any problem, you can chat you can just say anything. I will check my chat and I will respond. Okay. So, Ada Soalan, Ada Masahala, Ada Faham. Right. So like I said at the beginning, everybody should know the difference between elastic and plastic deformation. So do we all know the difference between elastic and plastic deformation? Yes, no.
Yes, sir.
Okay. Terima kasih, Mohammed Daniel. Terima kasih, semua.
Yes,
Okay, so let's continue. Now, the other thing I'm expecting you to know at the end of this class is that you should be able to derive stress and strain from experiments. Like I said at the beginning, you should be able to understand how to measure the stress and strain through experiment. So, and what type of experiment are you expected to carry out? For you to measure stress and strain, in engineering generally, we looked at what we call the tensile or compression test. Compression test. So in your class this semester, one of your lab is going to be tensile test. And during this test, we'll be showing you some things. But I think it's good that you are learning this before the lab. So that will give you a better understanding when you are doing that lab. So, like I mentioned, one of the most important tests to perform in order to check the tendency of your material to withstand load with no deformation is tensile or compression test. So you want to check the strength of your material. One of the most important tests is tensile or compression test. Both of them are similar. You have a specimen like this. Let me just give you a sample of a specimen. You have a specimen like this, okay? Now, let me draw it in two ways. So we have two specimens. Now, if I apply this load in this direction, I'll be pulling away from the specimen. This is tensile. If I apply this load in this direction, I'll be pushing against the specimen. This is compression. So basically, for tensile and compression tests, we use the same equipment. You use the same equipment for tensile and compression tests. The only difference is for tensile, you ask your equipment, you ask your what's it called, the load cell to move up move away from the specimen. Whereas for compression, you tell your load cell to move down against the specimen. So let's look at this. Okay, like I said, tensile or compression machine. So like I said, you use the same equipment. And this equipment varies from one brand or manufacturer to the other. It's unfortunate some of you are not yet in UTEM. Here in FTK MP, we have, I think, two brands. We have Instron machine in material testing lab, and in my Macma mechanic paper, we have Instron, and in the same material testing lab, we have Chimazo. So it could be Instron. These are different brands. Then there is Datec. Then we have Chimazo. So any of this. In UTEM, we have this. In FTKMP, we have this, but we don't have Datec. So like I said, this machine varies from brand to brand. Some of you are using iPhone, some are using Samsung, some are using Oppo, some are using Huawei. So it's the same thing with your in capacity of the load cell. The load cell will tell you the maximum limit. This load cell varies. I think we have 250 kN in material testing lab. we have Chimazu of 100 kN, and we have 600 kN instron in mechanic paper jar, magma mechanic paper jar. So different load cell. So for 50 kN load cell, you cannot test beyond 50 kN. For 100 kN, you cannot test beyond 100 kN. Same with your mobile phone. Some of you, the maximum, your RAM is 2 gig. And your memory is 16 gig. But for some, they are using 8256. For some, they are using 6128. So it depends on the brand and the capacity. So a typical tensor compression instrument machine is shown below. I think this was 250 kN, and that was at the University of Liverpool in the UK. But like I said, in FTKMP, we have about 2 or 3 instrument. We have 2 instrument machines, 50 kN and 600 kN, and we have Chimazu of 100 kN. So don't worry, anytime you come on campus, we may have time to go on some of those equipments. So like I said now, to carry out this test, here is your specimen here. Now, if you tell this machine, there is there is control here. This is up and this is down. If you move this up, then you'll be carrying out tensile. If you push this down, it will be doing compression. So the same machine can do the same, can do both tensile or compression, depending on the instruction you are giving. Now, for you to carry out your tensile or compression test, from now, I'll be talking more on tensile test, because your experiment is going to be tensile during your lab session. So I'm going to restrict myself to tensile, because again, tensile is commonly used as compared to compression test. So I'll be talking on tensile test from now. Tensile test. Now, for you to carry out your tensile test, there are few procedures you need to follow. There are few steps to follow. Step SATO. Your specimen must be machined or manufactured according to standard size and shape. There are 2 common shape we use. This is one. That is a round specimen. Then this is another shape. This is a flat specimen. But this is machined to standard. So the size and the shape is to standard. The same thing applies to this. For example, in your lab classes, step number 1, SUDA, they have machined all the specimen already. So they are going to give you a machined specimen. They just give you this specimen. You don't have to go and machine that. So like I said, your specimen could either be flat specimen like this, or your specimen is round specimen like this, a round coupon. Okay. Any problem before I continue?
No.
Okay. Step number 2. Now for your lab, you now start from step number 2. For your lab, you start from step number 2. Step number 2. Before the beginning of your experiment, you mark the gauge length of your specimen. So here I have this. Where's my marker? I'm going to mark it here. So between here and here is my gauge length. That is the distance between 2 marks. So I put a mark here and I put a mark here. Can you see my marks? Hello?
Yes, sir.
Okay, you can see. Okay. So you, at the beginning of your experiment, you mark your gauge length, which is a mark here and a mark here. This gauge length is taken as your original length of the sample, your strain values. So this gauge length, you are going to use it for your original, calculating your strain value. Then number two, step number 3. Now, after you mark, you need to measure. Now you measure the gauge length and the diameter. Diameter, if you are using this. If you are using this, you measure the diameter. If you are using this, you measure the thickness and thickness and width. But in your lab classes, you'll be using this one. This is exactly what you're going to use in your lab. So let's just discuss this. So you measure the diameter of the sample. So step number 2, you mark your gauge length. You measure the gauge length, which is going to be your original length. Then you measure the diameter of your sample. And for you to do that, you are going to be given some of this. So all you need to do is just wait, 1, 0, just measure. Then you measure from here to here. Finish. So number 3, if you have any problem, please let me know. Number 3, you grip your sample at the ends. You grip your sample at the top end and at the bottom end. So these are your ends. You have one grip here and one grip here. If you look at the picture we have earlier, you can see here, this sample is gripped here and is gripped on this side here. So this is top end and bottom end. So you grip your sample at the ends, then you apply a tensile load. Like I said, for tensile, you are pulling away. For tensile, you are pulling away from the sample. You are pulling away. Now, one thing I failed to mention earlier, now for this machine, all the chain, one end will be movable, the other end will be fixed. Now, depending on the brand and the machine, movable could be down, fixed could be up, movable could be down, up, or it doesn't matter. This could be movable or fixed here, or this is movable, this is fixed. But the most important thing is Satu end fixed, Satu lagi movable. So now, say for example, in this case, the fixed end is the bottom. You want to apply a tensile load, then you move away from this end. So you'll be pulling this end up, then you'll be moving away, tensile load. If you are pushing down from this, it will be compression. So that's what we are trying to explain here. Pulling the specimen away, you pull down. Then next, at frequency interval, like a table, you have load, and your load is either in Newton or kilonewton, and you have your elongation. Because it's tensile is elongation, it's going to increase. and you have your elongation in mm. So at 0 load, add a 0 elongation. At 10 Newton, console point, sato. At 20, console point, dual. At Tiga, console point, Tiga. At 40, console point, enam. At 50, console point, no, satu. Okay, you record. So at different interval, at frequency interval, you read the load and elongation. Okay, so you write down. Then number 5. Number 5, you need to change this load and elongation to stress and strain. Stress and strain. How do you change this to stress and strain? What is the formula for stress? What is the formula for stress?
F over A.
F over A. So your stress, wait, let's do this. So your stress equals F over A. Your F is your load. Your A is the area. And because this is circular, you measure your diameter already, which is pi d squared all over 4. So here, if I leave this now, so here now is going to be equals to 0 bahagi pi d squared over 4. Sini 10 bahagi pi d squared over 4. Faham tak faham?
Paham, sir.
Faham, sir.
Jadi
Faham
20
doktor.
pi d squared over 4. Ni 30 pi d squared over 4. Force over area. Force over area. Then 40 pi d squared over 4. Lagi 50 pi d squared over 4. Then you change your elongation to strain. So what's the formula for strain? Normal strain. Oops.
Delta L over L or L naught.
All I've written is gone. Oh dear. This thing take away my writing. Okay, your strain is equal to delta L all over L original. So your L original is your gauge length. You measured before your gauge length. And your delta L, already this thing is gone. How to do it? Okay, so I'll just try and see if I can do it again. Oh, why did it disappear? Because if I explain this one, you understand this one, then everything finish. We know everything already. Okay, so I will do that again if I can remember the datas. Okay, so what we have before is you have your load in Newton and elongation. We said 0, 10, 20, 30, 40, and 50. And this is 0, this is 0, 1, 2, 3, 4, 1. 1, 2, 3, 4, 2. 1, 2, 3, 4, 3. 1, 2, 3, 4, 6. 1, 1, 2, 3, 1, 1. Okay. Now we now say you need to convert to convert to stress and strain. Stress, which is F all over A. Okay. Please, if you don't understand what I'm doing, let us know. Then you have strain here. So let's do our stress, and we say this one is going to be equal to 0 divided by pi d squared over 4. That's our area. This is going to be 10 divided by pi d squared over 4. This is 20 divided by pi d squared over 4. This is 4 pi d squared by pi d squared over 4. Okay, everybody understand this, right? Faham ta faham? Hello? Okay, okay. So Lagi, now we need to change to strain, eh? What is the formula for strain, normal strain? Delta L all over original length. Your delta L is your elongation. So this is F. This is delta L. And your original length is your gauge length. So here now, this is equal to 0 divided by gauge length. At the beginning, you measure your gauge length, right? So here is going to be 0.00001 divided by gauge length. Here is going to be 0.002 divided by gauge to 0 is equal to 0.00011 divided by gauge length. So now you know your stress, you know your strain. Ada soalan?
Ada.
Ada. Okay. So like I said, you convert your load and deflection to stress and strain. That is the next thing. Then after converting to stress and strain, then you plot the curve of your stress versus strain. You plot the curve, you have a diagram of stress on the y-axis and your strain on the vertical, on the x-axis. Stress on the vertical, strain on the horizontal. So you have your graph like this. Then from this graph, then you can determine the mechanical properties of your material. So we'll be looking at one or two examples. Then with that, you'll be able to understand better. Okay, so like I said, the next thing is you plot your stress strain diagram. So here is stress and this is strain. So this should be in MPa or in Pascal, MPa or Pascal. And strain, no units. Now, depending on your material, the shape and size of your stress strain diagram will depend on your material. Now, for this one, this is more of my steel. This is typical of my steel. This is aluminum. So depending on your material, the shape will be different. For my steel or for metal, for my steel is different from aluminum. They are both metals. But depending on the material you have, the shape will be different. Now, on this shape, on this stress strain diagram, we are going to be looking at how do we determine the mechanical properties of our material. That's what I'm going to look at next. So before I go to that, any questions so far? Ada Suala, any questions
No,
so
sir.
far?
Oh, no
Okay.
question.
Yeah, answering
Hamza.
me no. Okay. So now, on this stress strain diagram here, where is the stress strain diagram? On this stress strain diagram, I'm going to draw one here. This is stress, and this is MPa, and this is strain. Why I'm putting this is many of my students, they are fond of not putting unit, and I always take their marks. So please always put your unit. You have this up here, then you have something here, then you go up. Like I said, this is my style. Now what you will discover is this go from here to here, a straight line. At this point here, there is a bit of a change of guard. Then after that, it goes up to somewhere here, then it goes down up to here. Now, on this stress strain diagram, there are 5 points that is of interest, 5 points. From here to somewhere here, 1. This is point number 2. Here is point number 3. Here is point number 4. Here is point number 5. So on the stress strain diagram, there are 5 points. Point number 1 is your proportional limit. Point number 2 is your elastic limit. Point number 3, which is this point here, is your yield stress. Point number 4 is your UTS, ultimate tensile strength. And point number 4 is your fracture stress. Now, what is the difference between point number 1 and 2? Your point number 1 is a point where your stress is directly proportional to your strain. How do I mean? Let's go back to the previous here. Okay, here. If you look at this, your proportional limit here. Looking at this table, your proportional limit. Hello?
Yes, Jose.
Looking at this table, where do you think is your proportional limit? Your stress is directly proportional to your strain. Now, look at this. 10 is producing 0.0001. Where you add another 10, it changed to 2. You add another 10, it changed to 3. There is a direct proportionality. Now you add another 10, it changed to what? It changed to 6, which means up to here is your proportional limit. Because at every 10 increment, you have 0.0001 increment of elongation. If you increase by 10, then it increase by 0.0001. You increase by 10, increase by 0.001. But after this point, you increase by 10, not the same any longer. Do we understand?
Yes.
I understand that.
So from here to here, your stress is directly proportional to your strain. So that is your proportional limit. Then here, that is the last point when your material can return back to its original position when you take off the load. That is the maximum point where your material can return back to original position when you take off the load. Maybe I just read from your lecture note. Okay, so like I said, there are 5 critical points. 5 are the Lima critical points. The LAM, your stress strain diagram. SATU, proportional limit. DUA, elastic limit. TIGA, yield stress. UMPAT, ultimate tensile stress or ultimate stress. Lima, fracture stress. So your proportional limit is the maximum point on the graph where the curve is perfectly linear. That is, your stress is directly proportional to your strain. The same increment in stress produce the same increment in strain. If the increment in strain is 1, 1, 1, your increment in stress is 5, 5, 5. 5 increment produce 1. Another 5 increment produce 1 is direct proportionality. So that is your proportional limit. Your elastic limit is the maximum stress that the material can sustain without any noticeable deformation on the material after removing the load. So that means when you remove the load, the material returns back to original position. That is your elastic limit. The maximum point, the maximum stress that your material can return back to original position is your elastic limit. Excuse me. Then your yield stress. Yield stress is the stress that can cause yielding of your material. That is the stress needed to produce a small amount of permanent deformation on your material. The stress required to produce a small amount of permanent deformation on your material. Then your ultimate stress. Your ultimate stress, where are we? Okay, from here now, your ultimate stress is the highest point. The highest point on your diagram, on your stress strain curve, and your fracture stress is the last point. That's the point where your material breaks. So your ultimate stress is the highest stress achieved on your stress strain diagram. The highest stress achieved on your stress strain diagram is the highest point on the stress strain curve. And your fracture stress is the stress at which the material fails. That is the last point on the stress strain curve. So if you go to your stress strain curve, the last point, this is the last point here, that is your fracture point. And the stress at that point is your fracture stress. Ada soalan.
Enggak ada.
Tiada, sir.
Faham tak faham?
Paham, sir.
Faham,
Okay.
sir.
Okay, sir.
So like I said, on the stress strain diagram, there are 5 critical points. SATU, proportional limit, dual, elastic limit, TIGA, yield stress, UMPAT, ultimate stress or ultimate tensile strength, Lima, fracture stress. Okay, again, on the stress strain diagram, there are 4 regions. Now listen, 1, 5 critical points. Dual are the 4 regions. 4 is it bahagian, eh? Bahagian is section, it's like a region. Okay, so you have 4 regions on the stress strain diagram. Now, where is my stress strain diagram? Let me go back a bit there. Oops, okay. I can draw here again. You have your stress in MPA. You have your strain, you go up here, up to this point, and you have this. Now, from here to here is one region. From here to here is one region. From here to your UTS is one region. And from your UTS to this point is another region. So this is region 1, region 2, region 3, and region 4. Your first region is your elastic region. Your region number 2 is your yielding. The region 3 is your strain hardening. 2, 3, and 4. Number 4 is called necking. So you have elastic region, yielding, strain hardening, and necking. So at the Lima point, critical point, Umpat region. Faham ta faham. Hello. Ada orang sana. Ada. So I think I should allow you to take 5. Then after that one will come back. So I'll be at 5 for the 4 regions. So I'll take 5. So by 1 o'clock I'll come. Is that okay?
Okay, sir. Okay, sir.
So let's take 5 by 5 by 1. Okay, I think by my time it's 1 o'clock, so I need to come back online. All right, so you're welcome back, guys. We need to continue from where we stop. Don't worry, we can just do it. Right, so I guess everybody is back. Hello, are we there?
Hello, sir.
Yes, sir.
Oh, great, excellent. Okay, so just before the break, I told you that we have 5 critical points on your stress strain diagram. Can you mention them one by one? Just type for me if you are ready. Ada Lima critical point, Tuli Satu Satu. Point Satu, point Dual, point Tiga, point Impact, point Lima. Just Tulis anyone you like. Ada Lima critical point, Tulis, Satu Satu. Who is typing? Type. Point 1. Ayo, Tada Orang. Sumotido. Proportional limit. Rima can say. Nuru. Mohammed. Okay, they are now rushing me. Mohammed Azaim. Elastic limit. Thank you. Fatim Fahana is repeating proportional limit. Okay, use stress. Oh, wait. Who is typing yielding? Skejab. Ada Satu Masala. Africa, I know. Yielding is not a point. Yielding is a region. At the Lima point, at the Impact region. Lima point, proportional limit, elastic limit, use stress, yes. Lagi, use stress. Fracture stress, okay. Fracture stress, ultimate stress, Logan, ultimate stress, thank you. So yielding is not a point. Yielding is a region. So please note that. At the Impact region. So Impact region now. Type the region. I want to see the regions. Regions now. I'm okay with point. Critical point. Okay. At necking. Terima kasih Nazri. Elastic region. Nuru Kairum. Okay. Nuru Iswain. Yielding. Thank you. So you have elastic region, you have yielding, strain, oh, Terima Kasih Semua. Very good, very good. Well done. So you have elastic region, yielding, strain hardening, and necking. So let me quickly explain, then we continue. Now, your elastic region is a region where your material can return back to original position. Your elastic region is the region where your material will return back to original position when the load is removed. And like I said, that is the deformation is temporary. Now, if you want to represent this using mathematical relation, your elastic region is a region where your stress is proportional to strain. Because in your elastic region, your material obey Hooke's law. And from Hooke's law, your stress is proportional to your strain. And your constant of proportionality is your Young's modulus. Your E is your Young's modulus. Now, if you make E the subject of the formula here, E is equal to stress divided by strain. You have your stress strain diagram. I have my stress and my strain diagram, and I have this line here. Now, this is my, let me say this is my elastic limit. From here to here is my elastic region. If I want to calculate my E from this region, it's just the slope or the gradient of this line. So the slope or gradient of the elastic line is equal to E. So your E is equal to delta stress all over delta strain, which is basically the slope of this line. So if you know the slope of this line, then you can get your E. So mathematically, it means the material obeys Hooke's law. And for Hooke's law, your stress is directly proportional to your strain. That is, your stress is proportional to strain. And the constant of your proportionality is E, which is your Young's modulus. So from the above equation, it implies that E can be determined from the ratio of stress and its corresponding strain in the elastic region. So within your elastic region, you can calculate the ratio of your stress, which is the gradient or the slope in your elastic region. Therefore, E is the slope or gradient of the straight line, the elastic region. So you go to your elastic region, you take the straight line, then you can calculate your slope. So if we have a stress strain diagram and we ask you to determine E, all you need to do is you go to the straight line, slope or gradient.
In the mean.
Here, tabulate. There you cannot. Who is that
Iya,
one?
Dek.
Amiru, can you mute your mic? Here, this is not a straight line. You cannot do here. But the straight line, bole. So you can do here, you can calculate your gradient or slope here, and you get your E. The second region is your yielding. Now, before your yield stress, your material will be behaving in the elastic behavior. That means it's going to return to its original position when the load is removed. After yield stress, your material goes into plastic deformation. That is, there's going to be a permanent deformation on the material. And if the stress, so if your stress go beyond your elastic limit, then your material deform permanently. So your yield stress is a transition between elastic and plastic deformation. The moment you get to yield stress, then your material goes into plastic deformation. Below yield stress, your material behaves elastic deformation. Then strain hardening. This is a region where the material tries to strengthen itself, try to defend itself against the applied load. In the plastic region, as your load increases, the material will try to resist, defend itself against the load acting on it, thereby straining itself, trying hard to withstand the load. Then when your material gets to UTS, at UTS, your material cannot take any other load. It has gotten to maximum, so it surrenders. So at UTS, your material surrenders. So when you now begin to apply more load on the material, then the material will fail eventually, because at that point, it just gave up. And what happened is when you get to UTS, necking will begin. What is necking? Some part of your material will become smaller as compared to others. Why do we call it necking? If you look at your neck is smaller than this side and is smaller than this side. So in between your material, it looks like a neck, very tiny. So if you look at this example here, you will discover that this region is smaller as compared to here. So here necking begins. So this region exists just after your UTS. Necking results when there is a reduction in the cross-section area at the point greater than the load arising from the strain hardening. And at that point of the maximum load, where you have your necking, there will be a decrease in the area in that area. And as your necking begins, the stress will be concentrated at the point of the necking, at the neck region. Thereby, your material will fail at that point, because it's going to dictate that this is the weak point of this material. I will concentrate on this, and your material will eventually fail at the point of necking. Okay. So we have 4 regions. You have elastic region, you have yielding, strain hardening, and necking. Right. Any question before I proceed? I still have a few slides to go. Any questions? Ada Soalan?
Tada.
Tiada. Ayo, sumo ora pai. Okay. Now I'm going to take you through something a bit different now. Now we'll be talking about your stress strain diagram. And if you remember earlier, I did something here. I'm trying to see where I did it. I wrote something before now. I think it's okay here. Now, let's look at this. Here, I try to calculate this stress. And I said for this point is 10 divided by pi d squared all over 4. Now, you remember that this d was the one you measured initially before the start of the experiment. Is that true? Here, you measure here. You measure your diameter here. So this is your d. Now, here your d is the d you measure before the start of your experiment. But the question is, when you do your experiment, is your diameter going to remain the same all through the experiment? If you do your experiment, is your diameter going to remain the same all through the experiment? When you pull this, do you think your diameter will remain the same at every point?
No.
No.
Okay. So one thing is sure, that your diameter is not going to be the same all through the experiment. But here we said your diameter is same, which means this stress we are calculating here is not true. It's not true. Okay, let's leave the stress. Let's go to strain. Now, when you pull, okay, we measure your gauge length. Again, your gauge length is here, L naught. And we begin your experiment, we are pulling. And your gauge length here is same as this one and is same as this one. Is that possible? Is your gauge length going to be the same all through the experiment? Is your gauge length going to be the same all through the experiment? Okay, look at these two here. I tested this specimen some months ago. Let me hold it at one end. I want to make sure you are seeing this experiment. The one at the bottom, this is the tested material, this is the original material. Is it the same? Is the length not true?
No.
When you pull, the length is going to increase. So which means here, the length here is not true. So here, not true. Now, in engineering practice, we have what we call the true stress and true strain. This one here and this one here is called engineering stress and engineering strain. The one you use the original length and original diameter is called engineering stress and engineering strain, or conventional stress and conventional strain. That is when you use the original diameter and original length. That's the one we have been using all day. Now, I've told you now, or we have been able to prove that this stress, this your engineering stress or engineering strain is not true. Then now, let me ask you a question. If I want to determine the true stress at this point, what do you think what do you think I can do to get the true stress at this point? If I want to get the true stress at 10 Newton, what am I going to do here? Hello? Hello, is anybody there? If I want to get the true stress at 10 Newton, what do you think I can do to get the exact stress at that point? There's nobody. Okay, now if I want to get the true stress at this point, what I can do is to measure the diameter at this point. When it's 10 Newton, I measure the diameter, then I can get the actual diameter at 10 Newton. Then to get the true stress at 20 Newton, I need to measure the actual diameter at 20 Newton. Then at 30, I have to measure the actual diameter at 30. And the same thing happens to strain. I need to measure the actual length, actual at those points. Or you call it instantaneous length. That is the length at instant load. The length at 10 Newton. The length at 20 Newton. The diameter at 10 Newton. So they are at instant loads. So now I'm going to differentiate between what we call the true stress and the true stress strain diagram and conventional stress strain diagram. That's why I've been saying all this. I want to differentiate between these two graphs. So generally, you have what we call the true stress, true strain diagram, and you have the engineering stress strain diagram. Like I said, the one we have been talking about all day is engineering stress strain diagram. There is a difference between the conventional or the engineering stress strain curve and the true stress, true strain curve. Now, the basic difference between them is for conventional stress strain diagram, you use the original cross-section area and original length of the specimen to calculate your stress and strain. So for conventional, you use the original cross-section area, which is the original diameter, and the original length to calculate your stress and strain. Whereas for true stress, true strain diagram, you use the cross-section area, the actual cross-section area, which is the instantaneous area. That is the area at instant load. And your instantaneous length, the length at instant load. For example, length at 10 Newton, you measure. When you get to 20 Newton, you measure the length. But why are we in engineering using the conventional? It's easier to use the conventional because if you have to test all your specimen and at every instant load you stop and measure, it's going to take you a longer time. An experiment that should take only 1 hour could take you 1 day because you need to stop, measure, you stop, measure, then you stop, you measure. Even after some time, you'll be tired. So what we do is we use the conventional stress strain diagram. Then if you have the conventional data, you can convert. You can convert your conventional stress to true stress, and you can convert your conventional strain to true strain. To convert your conventional stress and strain diagram, you use this formula. Okay, so your true stress is F all over instantaneous area, and your true strain is L all over instantaneous length. Now, if you want to convert from true stress from conventional, this is your conventional stress or engineering stress. If you want to convert from engineering stress to true stress, all you need is your true stress is equal to your engineering stress into 1 plus your engineering strain. So if you know your stress and strain, then you can get your true stress. And your true strain is your natural logarithm of 1 plus your engineering strain. So if you know your engineering strain, then you can get your true strain. So all you do is, in practice, you do your conventional stress strain, you plot your conventional stress strain diagram, but you can now change from conventional to true stress and true strain. From your conventional stress or your engineering stress, you can change to true stress, and from your engineering strain, you can change to using this formula here. Ada soalan. Ada soalan.
Ada, sir.
Oh, this student, they understand everything, eh? Very intelligent student. Okay, so if there's no question, let's quickly continue. Now, I'm going to go into other things. I believe you've heard about this before. Let me write. Ductile material, ductile. And brittle material. Have you heard this before? Ductile and brittle material. Have you heard about it? No? Yes?
I don't think so.
You have heard about ductile material and brittle material. So you don't know the difference between ductile and brittle material? Who said I don't think so? Okay, what's the difference between these two? Difference between ductile material and brittle material.
Rapo.
Who is talking? If you are talking, you say, well, I understand.
Brittle break easily.
Okay, somebody is talking here. Brittle break easily, easy to fracture as compared to ductile. But somebody said, I don't think so. Okay, so brittle break, oops. Ductile and brittle. So somebody said this one break easily. Okay, let's go. Any other one? Doctor is brass. Okay, why is it brass? Logger. Doctor, I know, thank you. Logger, thank you, but why is Doctor brass? So we have brittle material and we have ductile material. Yeah, one break easily. What about this one? Okay, let's just use the opposite of this. If this breaks easily, then this is hard to break. That's opposite, eh? Okay, what other thing? Yeah, able to deform, wait. Able to, Moses, able to deform without losing toughness. Which one is that one? Which one is able to deform without losing toughness? Brittle material do not show deformation. Okay. Okay. Okay, in terms of the fracture surface, let's look at the fracture surface. In terms of the fracture surface, how does it look? Mohammed Zarif is saying can deform without breaking, and this one are hard but can easily break it. Okay. In terms of the fracture surface, how does it look when you break a brittle material and you break a ductile material? In terms of the fracture surface, how does it look? In terms of fracture surface, how does it look? Brittle and ductile material. This is going to be rough, and this is going to be smooth. Now, why is this like this? Why is brittle material hard to break and is rough when you break it? And why is brittle material easy to break and is smooth? I'll be looking at that now. Ductile and brittle material. Ductile material are materials subjected to large strain before failure. So when you want to break it, that's why it's hard, because it's subjected to large strain before failure. So it goes from here, it goes past your elastic region to plastic deformation, then it went, so it's subjected to large strain. Then you, example, like somebody said, you have brass, you have mild steel, yielding. It goes up here, it cut off, bam, break already. So for brittle material, there is little or no yielding. So for ductile material, it undergoes, whereas for brittle material, it goes through elastic deformation. So for brittle material, there is little or no yielding before failure. An example are gray cast iron concrete. They don't have a well-defined tensile fracture test due to random appearance. So for brittle material within elastic region, break. For ductile material, it goes from elastic into plastic deformation. So it undergo large strain before failure. Right, okay. Is there any question with that? Other Swala?
No questions, sir.
Hello? Okay. Now, I showed you something earlier. I told you before now that you have 5 region or 5 critical points on your stress strain diagram. I want to plot 2. Okay. So this is my stress. I go up here, then I have this one, and I go up here. I have now this one, and I just have like this. Okay, here you have your, where's your yield here? I have 1 point here. Let me put a point here, a point here, a point here, a point here. 1, 2. And this is B. Now on A, where is your yield stress? Is your yield stress?
Number 3.
Number 3. Okay, somebody said this is yield stress. Okay, thank you, sir. Now let's go to B. On B, where is your yield stress? Let me say I have one here. It's difficult
No
to
use
predict
stress.
where one. Where no use stress. Who says there's no use stress? Okay, yeah, I can agree with the person that said there's no use stress, because in this case there is no clearly defined, well-defined use stress. Afif, you are requesting something, but I'm going to decline. Okay. Okay. Now, here there is no clear use stress. But does that mean that there's no use stress? No, there is use stress. But the use stress in this case is not well defined as compared to this. Here we can pick that this is our use stress. So easy. Fine. So if we have a specimen or we have a material with no well-defined use stress, how do I define the use stress? For you to define the use stress, we use what? Proof stress or offset stress. Some people call it proof, some people say offset stress. So the next thing I'll be explaining is how do you determine your 0.2% offset stress? So offset use stress. Some metals do not have a well-defined yield point. In this case, the offset use stress can be determined by the stress corresponding to the intersection of the stress strain curve and a line parallel to the elastic line by a specific strain, normally 0.2%. How do you do this? I think I have to explain with this. Okay, you have this here. I'm going to put some values now, okay? You have this and you have this. This is my line and this is this one. This is 0.001, 0.003, 0.004. 0.006. Okay, that's enough. Now, I want to determine my 0.2%, 0.2% offset. What does this mean? This is 0.2 divided by 100. What does that give? What divided by 100? 0.2% is 0.2 divided by 100. What is that? I need somebody to press calculator. I don't have time. 0.2 divided by 100. Where are they? Hello. Thank you. Nuru. Terimaka say 0.002. So now for you to determine your yield stress on this graph, you go to your strain line. Then you look for 0.002. Cine. Okay? Then you draw a line parallel to your elastic line. So this line here must be parallel to this. So this point here is your yield point. So here you cannot get here your yield stress. So first you calculate your 0.2%. You go to your strain line on the strain 0. You draw a line parallel to this elastic line. This is your elastic line. Wherever you are touching the graph here is your yield stress. So that's what we are explaining here. So here you determine the stress corresponding to an intersection of your stress strain curve and a line parallel to the elastic line by 0.002. So here you can see here, this is my 0.002. I'm drawing a line. This line is parallel to this line, parallel. Then here is my yield stress. Any problem with that? You don't understand? You don't faham? Hello? Ada Swala, Ada Masahala. Masahala. Logan is okay. If Logan is okay, Logan speak for everybody. Okay. Now, let's look at fracture stress. Like I told you earlier, your fracture stress is the last point on your stress strain diagram. The last point on your stress strain diagram. Now, one of the things you will be asked to do in your lab is to measure the ductility of your material. How ductile is your material? How do I determine the ductility of my material? Like I told you earlier, ductile material can undergo large straining before deformation. So your ductility is the ability of your material to deform plastically without fracture. That is, deform within the plastic region and undergo plastic deformation without fracture. And for you to measure the ductility of your material, you can use two methods, either the percentage elongation or the percentage area reduction. Now you need to understand that when your material is increasing, the area will be reducing, the diameter will reduce. So it's either you use percentage elongation or percentage area reduction. To use percentage elongation is going to be delta L all over original length multiplied by 100. Because your delta L is equal to L to LF. And to use percentage area reduction is your original area plus original final all over original or original area multiplied by 100%. So you need to measure your final length and your final diameter. That one I did not mention before. At the end of your experiment, you need to measure your final length and your final diameter. you will be able to calculate the ductility of your material. Right. Let for a few seconds. Let me allow this student to check out there. Soalan, masalah, ada soalan, ada masalah. Hello? Ada soalan? No, okay. Okay, if there's no soalan, you have a question here. You have a question to practice. We have just 5 to 10 minutes to practice this. You have a tensile test for my steel carried out on the flat like this. And the resulting diagram, stress strain diagram, is presented in the figure below. Now they want you to determine Chari, modulus of elasticity, Chari, 0.2% offset yield stress, Laggy, ultimate stress, Dan, fracture stress. Now, before you begin to Chari, on this graph, on this plot here, we have two graphs. Ada satu hitam, satu lagi biru. Apa difference? Ada dua graph, satu hitam, satu biru. Apa difference? What is the difference between these two graphs?
Yang hitam tu ada linear graph.
As I better speak English so I can understand you better. I understand what you said. You said the hitam there is no linear graph, but I always encourage my students to help you. All right. So you said there's check up. Who is talking? Go on.
What's it?
Okay, black line have
Yeah.
a elastic limit. I don't understand that. What is the difference between the black line and the blue line? I want to know.
Black line, there is no linear line.
Okay.
And the blue line have linear line.
Okay, thank you, Azaim. I think that's good enough for me. Now, what happened here is this is a zoom out of this. Like Azahim said, for the black line, there is no linear graph, there is no elastic point and all this. So what we decide to do is you go from here to here. Okay, from here to here, then we zoom out. So if you look at this here, you have ada dua scale. Satu atas, satu lagi bawah. Atas hitam, ni bawah biru. So ni zoom, you zoom out, then you get this. So from here to here, we change out, then you get this one. So now the is only from here to here only, whereas the black line is the entire curve. Why do we zoom out? Because the black line has no linear graph. There's no elastic point. You cannot see. Here is difficult to determine your elastic, determine your 0.2% offset. We zoom out. Understanding. Now I want us to look at these 4 questions. Which one do you think is more easier to do? 1, 2, 3, 4. Now look at the 4 questions. Chari, modulus of elasticity, 0.2% offset yield stress, ultimate stress, Dan, fracture stress. So which one is the most easiest one to do? Easy la. Where is Sarah? Sarah. Oh, Logan is going for yield. Oh, come on, Logan must be very intelligent. So which one is the easiest one to do? Where is Sarah? Sarah. Let's talk. Which one is more easier to do for you? We need to finish now. Nosera Farisha Binti Mohammed Isa, where is she? Everybody is going for 2. 2 is more easier for Iswan, it's more easier for Logan. Okay, that's interesting. Where are the others? City Mash Maba is it Mabash? What is her name? City Masba. Which one is more easier for you to do? Guys, come on, let's talk. We need to round up. Two. Okay. Everybody is going for 2. Okay, so he said 2. I want you to determine the offset use stress. Okay, let's go. Now, wherever you are, I want you to determine the offset use stress. Since everybody is going for 2, Logan is going for 2, and the rest. So let's determine the offset use stress for this graph. So I want to see your answer. Just determine your offset use stress and type for me. I just want to see your answer. Yep.
Sir, can
Yes.
when we zoom the black graph, we see the blue graph, right?
Yes.
All right.
So for you to determine your offset use stress, you use the blue graph and the scale Bauer.
Oh. All right.
For you to determine your modulus of elasticity, you use the blue graph and the scale Bauer. But for you to determine your ultimate, you use the black graph. For you to determine your fracture stress, you use the black graph. Okay, so now determine your offset yield. Now I've changed. Let's start with offset yield quickly. I want everybody to determine the offset yield stress. Mazdika, if you are there, just say yes. Offset yield, okay. So from the graph, okay, go on. Mazdika, if you are there, just answer so I can mark your attendance while you are doing that. Mazdika, Ubong. Megat Iskandar.
Yes, sir.
I'm here, sir.
Who is there? Who is that one?
Mas Dika Ubong.
When I called your name, you don't answer. Mohammed Fahan Fidaus. Just continue.
Yes, sir.
I want to. Okay, thank you. I want to see your offset use stress. Then we continue. Mohammed No Ikmal bin Asmadi.
Yes, sir.
Okay. Mohammed Shafiq bin Bakri.
Yes, sir.
Okay. So offset use stress is 220. Mohammed Adam. Adam is getting 220. Thank you, Adam. I'm waiting for others. Adam, thank you. Mohammed Azik bin Baharuddin.
Yes, sir.
Azik Baharuddin, thank you. No Iswan, thank you. I'm waiting for others. Azik bin Cairo Anwar.
Yes, sir.
Iswan Ayman,
Yes, sir.
where? I cannot see.
Yes. Yes, I'm here.
Nasmi bin Abdul Abghani. Nasmi. Thank you, Mohammed Daniel. I'm waiting. Nasmi. Nasmi. Adam, I think Adam is there. Don't worry, Adam. I think I've seen you before. Amiruddin bin Roslan. Amiruddin. Amiruddin bin Roslan. Thank you, Mohammed Aman, 221. Amiruddin, where is he? Amiruddin is not here. Nick Ahmed Nazran, Nick Ahmed Nazran. Thank you, Shafiq. Nick Ahmed Nazran. Okay, thank you. Yeah, I can see you. No Shuhada. No Shuhada. Okay, now guys, thank you for that. Can you go and calculate your modulus of elasticity? Modulus of elasticity. Now, Nuru Chiron Nesia. You.
Yes, doctor.
Okay. City Masba is there. Visvan.
Yes, sir.
Vis. Okay. Okay, so Nasmi is absent and Amiruddin. Now I want you to go and calculate your Young's modulus, guys. Let's go. Let's go to group number 2. Group number 2, Fazwan Anafi.
Yes, sir.
Okay. Nazahim bin Zabidi.
Yes, sir.
Tajuddin, I think I saw that one. Kairu Fazli.
Yes, sir.
Okay. Abu Uzaifa.
Yes, sir.
Okay. Afif.
Yes, sir.
Afik. Afik bin Mohammed Arif. Mohammed Amal is calculating Young's modulus and he got 214.3. Thank you, Mohammed Amal. I'm waiting for others. Afik bin Mohammed Arif. Mohammed Afnan bin Azri. Afnan bin Azri.
Yes, sir.
Okay. Thank you, Nosera. Very good, fantastic. Well done. Thank you, Nuru Shuhaida. Thank you. Mohammed Amiru Amin.
Yes, sir.
Okay. Ikma.
Yes, sir.
Zat Azim. Is that Azim?
I'm here, sir.
Lukman